Huzzah. All right. So today what we're going over is subsidence and soil, the sinking of the land, bad foundations, everything that we kind of think about when we think about soil here in Texas. Freeze this. All right. We're going to go through some of this pretty quickly because we've already been over soil and subsidence, and so we want to get to the part where it really talks about how this affects us as humans and what the kind of hazards are from this. So they're going to start off with one slide about Venice sinking. We will talk about Venice sinking towards the end of the PowerPoint. But know that it's sinking pretty fast. It's sinking at a rate of 1.5 millimeters per year, which doesn't sound like much, but when you add this up over decades and you combine this with rising sea levels, Venice is getting flooded much, much more often. You can find plenty of videos online today of like the shops being flooded in Italy, or in Venice, sorry. People walking around with their pants kind of curled up so they can keep them dry. And it happens pretty often, sometimes just with a high tide, sometimes with a storm combined with high tides, but it's been a big deal. Obviously, Venice has the canals, and they live right there on the water. And on top of that, they're already kind of like reclaiming land that probably shouldn't be above water. And so this is a little bit of both. This is nature kind of infringing upon where humans have built all their stuff, but also in this case, humans building their city in an area where the city probably shouldn't be. So it works a little bit both ways. But frequency of floods have increased, and they've been spending a lot of money to try to keep that from happening. So getting into the chapter proper, they start with talking about soils, soil development, how soils develop, layers in the soil profile, so your different types of layers all the way down to your bedrock. They go through some details of those soil layers. Here's another like cutout illustration of the different soil layers. And we went through these last year, so I'm not going to spend very much time on them. And to be fair, it's not really important to what soil and subsidence do to humans when things go wrong. So they get through a little bit through a particle size, clay versus silt versus sand versus gravel, and you can even go bigger than that. And then they have their wonderful three-way chart, which is one of my favorite charts. I really like three-way charts, but you have percentages on each side, percent of clay, percent of silt, percent of sand, and you pick one location, and this dot would be in the loam category, and as a loam, it would have 45% sand, 20% clay, and about 30, maybe 35% silt, if that adds up to 100%, I think it might. So yeah, that's what we're looking at there. So again, different types of grain sizes inside of your soil, how it breaks up, what kind of look it has when it breaks up and it's dry. These are your different types of soil structures. Let's see, different types of developed soil. So weakly developed versus moderately developed versus well-developed. Well-developed is going to have better minerals in it and a better structure for growing. Weakly developed is going to be relatively young and not really have great mineral structure or overall development. So let's see how saturated your soil is, the moisture content, how much the water flows, whether it just soaks in or if it can flow from one pore to the other. And so this is showing a partially saturated soil. It's got a couple little air pockets in here, which in general is pretty good for growing. Some soil taxonomy, so different names they use for the soils, engineering classifications of soils, how much weight they can hold. And so you can see we can get into very, very complicated terms when it comes to soil. Soil study is almost like a whole separate branch of geology all on its own, as well it should be. Like everything that we eat has to come out of the soil or has some sort of association with the soil. And Everything that we build is on some sort of rock or soil. So knowing kind of the details and all the different types of soil is pretty important. Here, what is this one? Unified Soil Classification System. So they're going through some different types of materials. They say soil, but you're looking at gravels, different types of gravels and sands in here, and clays. Can agricultural systems maintain and improve soil fertility while minimizing erosion? The answer should be yes. You just have to work hard towards it. So in a lot of different industries, we're trying to be more conscious of soil, where the soil is going, what kind of minerals or pollutants happen to go into the soil. We all, even though it's very far removed, we all grew up watching short video clips of the Dust Bowl and how bad the Dust Bowl was, and the like lines of food, the food lines in the Great Depression / Dust Bowl. So we don't want that to happen again. We want to kind of keep everything running efficiently and well. So we try to keep an eye on this and understand what's going on. So now, introduction to subsidence and soil volume change. And so remember, when we talk about subsidence, this is based on the word subsiding, which is describing something sinking. And so when we talk about subsidence in soil, we're talking about your ground literally sinking underneath you. And there's a couple things that can happen there. You can have the ground beneath you dissolve, so dissolution of rocks beneath the surface, thawing of frozen ground. We don't really have that here in Texas, but if you move further north, there's tundra. The ice is going to take up a certain volume. If it starts to thaw, that volume is going to shrink down, and you could have subsidence happen. Compaction of sediment, earthquakes, and draining of magma. There's all sorts of things that can kind of contribute to the bottom of your land kind of dropping out from underneath you. The big thing, soil volume change, this does relate directly back to Texas. We have bad foundations here. Lots and lots of houses have bad foundations. It gets very dry in the summer and everything dries up. And then in the spring or the fall when it rains, we get these clays that expand with the moisture, and that shrinking and expanding or volume change causes a lot of problems for the foundations here in Texas. So this is probably not life-threatening. Yeah, unless your house just gets really bad and you ignore it and it collapses around you. This is not life-threatening stuff, but it is one of the most widespread and costly natural hazards. If you think about just foundation issues as a whole, we spend billions and billions of dollars every year just on foundation issues in the United States. And so add in a couple other things and you could really push that price tag a little bit higher and say that this is very, very costly. So we're going to talk about karst for a little bit. Karst is actually pretty cool. Karst is one of the first things I did a scientific poster on, and I've done not quite a bit, but I've done a little bit of work with karst. And what a karst is when you have the ground underneath you kind of dissolve away. And so when we talk about karst, in general, it's just going to look like a little hole on the ground. But karst, big karst and big karst systems can lead to caves. If you've ever explored around in an underground cave, that likely has some sort of association with karst. I know I've said this before, but if you ever get the chance to visit a cave, go and visit the cave. Caves are super cool. You will have a good time and learn some stuff too. So basically for karst, you have to have something dissolved. Water is going to come through and it's going to dissolve your rock, either a limestone or some sort of salt package, gypsum. These can be dissolved by rocks or by water pretty quickly. If your dissolved part just stays underground, you have a cave. If the dissolved part comes up near the surface, you get this little pit that we call a karst. So karst is like a pit that you see at the surface. And they have some images of these. You just see all these little like divots and holes pretty much everywhere. That's because underneath each one of these, there's been a little bit of rock dissolved out from water underneath it. There's a couple houses right on the road out here by the high school that have some small divots in the yard. You can really see them when it rains. There's like a bunch of small little puddles. And I wonder if that's like a karst thing or if they just had like an overactive dog that dug a bunch of holes in their yard. I don't know, but it's interesting when you kind of see the features, you're like, oh, I get that. So they're just showing you a time lapse in a way of how karst forms. I have a limestone rock package or something that will be dissolved by water relatively easily compared to some more robust rocks. As the water flows and it sinks down into the soil, it will penetrate into some cracks. The more it penetrates, the more it dissolves, and these cracks will start to get bigger and bigger and bigger, and you get these like sinkholes that form in a way. If my sinkhole doesn't come up to the surface, I get a nice cave that can have stalactites and stalagmites. And if eventually the water level drops down and the cave isn't flooded, I can go down there and explore it. So they talk about sinkholes. Your two basic types of sinkholes are solution sinkholes and collapse sinkholes. So in the solution ones, it just dissolves all the way up to the surface from the get-go. So like there's a crack from the surface, it dissolves, it opens it up. The collapse sinkholes, it would open up like a cave underneath, and eventually the roof of the cave gets too thin or something heavy gets placed on top of it, and it actually collapses down underneath. So both of these are going to be bad for your house or your foundation or in general just being near. But the collapse ones are definitely a little bit more dangerous because you never really know that it's going to collapse. So that's what they're showing you here. You have the cave that fills up with the water. The water's dissolving the cave away. And so as the water stays there, the cave just gets bigger and bigger and bigger. And then ultimately this arch up top gets too thin. The rocks are fractured, and gravity will take over and collapse everything down inside. That also could be aided by the groundwater kind of subsiding. So the groundwater has gone down a little bit, which relieves a little bit of that pressure. So which one came first? I don't know from this picture, but yeah, you want to be aware of that. Cave system. So again, you got your stalactites, you got your stalagmites. It's all about water. Water had to dissolve the cave away. And so it's not surprising that when the water drips from the top of the cave to the bottom of the cave, it leaves a little bit of the rock that it's dissolved away behind in the stalactites and the stalagmites. So know the stalactites and stalagmites. We're all familiar with those. Know that if they connect together and your stalactites and your stalagmites touch, it just is called a column. So they refer to columns a little bit that way. And if you have a big piece of stone that isn't pointy, like a stalactite, they're just going to call that a flow stone because it's kind of flowed out of the water. So let's see, tower karst, disappearing streams, and springs. So a tower karst is actually kind of a reverse karst in a way. Well, there's different ways they can form. You can have a big piece of rock that is a little bit less soft and erodible. And so when everything else erodes around it, this is kind of left in the top. Now, what happens sometimes, and these are a little bit big, so I'm not 100% sure exactly how these formed. Because if they formed like I'm about to describe, that would be pretty impressive because they're huge. But what happens sometimes with these karsts, I'm going to draw a little picture real quick. So I have my ground level, and I have like a crack in here. And it's going to fill up with water. The water is going to slowly dissolve stuff away. And eventually, I'm going to get this like karst sinkhole, right? So I have my sinkhole, my karst that happens. Then what can happen is, if I have erosion somewhere else, water is going to flow into this hole. And with it, it's going to bring sediment. And so slowly over time, I can have sediment fill up this hole. And if I wait long enough, the entire hole can get filled up with what essentially is a different type of rock. It's a red rock instead of a green rock. Does that make sense? It's a different type. Now, if that type of rock is a little bit more resistant to weathering and erosion, as my weathering happens, and this layer just gets kind of eroded away and goes down, 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 further down. This red rock will be kind of resistant to what's being weathered and eroded, and you will kind of have this surface feature with this big like jutting tower of rock that doesn't really look like it should be there. And that could be one of the things that has happened here. You could have a big piece of rock that used to fill in a hole, but now this rock is actually harder than the surrounding land around it, and when it gets eroded away, we have this kind of column of rock that's left over. These things actually, the work that I did with them, just to tell you real quick, the work that I did with them had to do with oil and gas. And so the problem is when I have this hole that's been filled in with a different type of rock. So I've got green rock everywhere. And then I have a completely different type of rock in the hole. When I send seismic waves through, the seismic waves, as they travel through this layer, will travel at a certain speed. And as they travel through this layer, they will travel at a different speed because the rock has a different density. And so when I get my seismic readout, what I will get is this kind of little deepening effect here. And so we can see the karst. When we look through the seismic readouts in the underground, we see the karst. But the question is, how deep is that karst? Is it actually this deep? Is it actually deeper? Or is it actually more shallow? And if I'm drilling through it, or if I'm trying to drill into it to see if there's oil and gas, knowing how deep it is actually kind of important. So one of the things I was working on with that is just trying to figure out from the data, is what I'm seeing really what is there? Is this tower this big, or is it actually this big, or is it maybe one of these small ones down here? When it's all underground and buried, it's kind of hard to tell, and you have to know what kind of data you can trust over here and what kind of data you can't trust and why. And that was kind of the poster that I put together. So that was a pretty interesting thing. Let's see. Thermokarst. So in high altitude regions or polar regions, your permafrost can exist most of the year. And then if it starts to melt, it's going to create a shrinkage, a reduction in volume that can lead to like a karst situation. So when the permafrost thaws, it can create land subsidence. Your land kind of drops down in a specific location, and you get these karsts, which are caused by heating and thawing, which they call thermokarst. Let's see, sediment and soil compaction. So your fine sediment is going to be able to collapse pretty well. Collapsible soils have dust deposits, loess, which is like wind-blown kind of sand and dust. Stream deposits in arid regions are bound with clay or water-soluble minerals. Water-weakened bonds cause the soil to collapse. Organic soils, wetland soils contain large amount of organic water. Okay, so what they're describing here is basically certain types of soils that have high clay content. Clay content is going to soak up a lot of water. When it soaks up a lot of water, it's going to expand. So clay-rich soils expand in size quite a bit. And clay soils, when you get them wet, really don't hold up very well. Has anybody done clay in art class? If you ever mess around with the clay in art class, you get it too wet, and it will just turn into like soup. It loses all structural kind of strength and cohesiveness. And so if you get a clay soil too wet from too much rain, it really loses its structure and begins to collapse. What do they have here? Land subsidence after an earthquake. This is literally just your land dropping down because of the strength of the earthquake, because of the movement of the land that you have there. Magma and lava tubes. So if your volcano erupts, let me go back. If your volcano erupts and allows a lot of lava to flow out, the tubes that carry the lava when your volcano is done erupting should be more empty. And so as that lava kind of sinks back down into the surface, you get these emptied out lava tubes, which I've talked about before. We've seen pictures of them. I told you that there's a good chance that the first moon base is in a lava tube, which we'll see what happens. Expansive soil. So like I said, if you have a clay-rich soil, when it gets wet, it will expand, and when it gets dry, it shrinks. And that's what we have here in Texas. That's why a lot of us have foundation problems, or are trying to not have foundation problems. And so there are things you can do, especially in Texas. You want to keep an eye out for different signs that the ground is moving. They have a little drawing here, but here is actually a really good sign. If you're driving around a neighborhood and all the sidewalks are jacked up, like the little pieces of concrete that they poured aren't level, you can see you have like a little sink down right here. And this little sink down, if you think about it, it's not supposed to be here. There's not a drain. And so when it rains, the water's not going to flow over this other hill. You're going to have like a puddle that just sits here. And so this is an indicator to me, when they built this street and the sidewalk, everything was just flat. And now I've had some sinkage here, so I can guess that, 20, 30 feet over on this lot, I'm probably going to have similar issues. Doesn't mean that I shouldn't buy a house here, I shouldn't build a house here. It just means I want to be aware of that and make extra certain that I'm taking care of my foundation and keeping problems from happening. Same thing here. Large cracks in the driveway, that's going to be a big red flag. Doesn't necessarily have to be an issue. I will say this is a rather curved driveway. It's on a hill. Just because you have cracks in the driveway doesn't mean there's foundation problems with the house. But I'm definitely going to have somebody extra check that, and I want to find out what I can do to keep those cracks from getting worse. You definitely don't want them going up into your garage and into your house. Let's see, frost susceptible soil. So soil containing water. Water is going to expand when it freezes. When the water expands, the soil expands, and we get what we call frost heaving, which is movement due to frost conditions. So they have three conditions for that. Temperatures must remain below freezing long enough to form ice. Water must be present to create the ice, and a significant portion of the silt-sized particles to allow water to be drawn through and retained in the soil. So I need a water-rich soil. And then once it freezes, you're going to see that big expansion from all the soil. And then once it thaws, you're going to see a drop down in the level here. Obviously, this is out in the wilderness. This isn't going to cause a huge problem. But after it thaws, that's going to be a pretty significant hole. And so if you're walking around or driving through here, you could hit a pretty big little bump there. So let's see, geographic regions at risk for subsidence and soil volume change, pretty much everywhere, roughly about 25% of the United States. Unless you're living on pretty solid rock, you're going to have problems from this. So a lot of Texas has this, a lot of the southeast kind of area in the eastern seaboard, Puerto Rico, most of Florida is going to have sinkhole problems and karst problems. And permafrost covers more than 20% of the world's land surface. So if you're living up in the north in that area, you can have a lot of problems from this too. So this is just showing you a couple different problem areas in the United States. If you've got organic rich soils, you're probably talking about New England or Washington State or Alaska. Coastal wetlands, Florida, some California coastal areas, Louisiana, North Carolina. Expansive soils pretty much everywhere. You can get swelling or drying depending on what part of the world you live in and how they built your house. Let's see. So yeah, here's your karst map. Not everywhere in the United States, but there's not really any states other than maybe, is that Minnesota? Other than Minnesota that have skipped out on the karst problem. So Texas, we got a lot of karst here in Texas. Florida has a lot of karst, and pretty much it's spread a little bit everywhere over most of the states. So this is it's not a dangerous issue. There's not a lot of people dying. There's some people that die in Florida every year from sinkholes, like it opens up underneath their bedroom or they drive their car into it. But outside of those freak accidents, generally it's not taking any lives. It's just costing us a lot of money and a lot of time and a lot of work. So effects of subsidence, sinkholes are going to be a thing. Changes in groundwater conditions, so where the water goes, how clean or impure it happens to be. Damage caused by melting permafrost, coastal flooding and loss of wetlands, damage caused by soil and volume change. And so now they're going to go into each of those. Sinkholes are obviously a big deal if it happens to you. It's not super widespread. In Florida, they do spend a lot of time and money fixing these. You can see how big this is. This is not a small sinkhole. That's a pretty large building. These are pretty large buildings here. There's a whole parking lot over here. And so this sinkhole is probably big enough to swallow this entire school, if I had to guess. This one looks like a sinkhole that formed right underneath somebody's house. They actually had to tear the house down. I know not too long ago, a sinkhole literally opened up underneath this guy's bed while he was sleeping, and just the earth swallowed him whole. And the sad part is when you fall into a sinkhole, it's very difficult to recover your body. It's like down in the dirt, and they're not going to send anybody down in there. And so if they can dig you out, they will, but sometimes they cannot, and you're just kind of lost. Let's see, changes in groundwater conditions. Caves create direct access between the surface and your groundwater. And so a cave can kind of help bring groundwater to the surface. I think somewhere in here they talk about springs, and where a spring comes to the surface, you probably have some sort of cave system that's related to that, just because water flowing through the ground is going to dissolve things and create little caves. The cave people to me are nuts. I mean, I get exploring and everything, and like I definitely would stick my head and maybe even my whole body in there. But at a certain point, I'm turning around, and I'm not going to be in there like a mile into some secret cave. No way, no way. But more power to you if you're a cave explorer. That's just not for everybody, I guess. I've seen too many scary movies. So permafrost has not remained frozen. This is damage caused by melting permafrost. So it melts. You have some volume loss in your soil, and it can cause a big deal. I mean, we can all guess what country this is, right? The like blockhouse kind of apartments. And we're talking about freezing permafrost or melting permafrost. This is Russia. This is Russia. And the Russians count on their ice to remain frozen. And when it doesn't remain frozen, apparently literally the entire corner of your apartment building can fall off because that's a Russia thing. On top of that, I warned them. Well, I didn't warn them, but I warned you, and now you're warned. Look at that sidewalk. That's a jankety sidewalk. And so someone should have seen the sidewalk and known there's going to be a problem here. If the sidewalk's bad, surely the ground that's underneath this huge apartment complex is going to be bad. What do we got? Coastal flooding, major effects of coastal flooding. You can see the foundation of this house has been moved. It is not where it used to be, which is a big problem if your house moves. So damage caused by soil volume change, one of the most costly natural hazards. It's not in big events, but it happens slowly over time all year long, and it does cost a huge amount of money. Hello? Yes, he's already closing his Chromebook. He must have been expecting you. Okay, no problem. To the gym, Andrew. What are you doing in the gym? Huh? Oh, really? Are they doing that today? All right. Well, good luck on your tests. They know y'all got all wild at prom, so they're just checking up on you.
Is that Alexa?
Hey. Okay. Okay, so frost action on roads costs about, why is my ringer on? What is going on today? Okay.
I'm glad y'all wore sweatpants.
Hold on, I'm reading the text from my wife.
Y'all suck. I'm going home. Seriously. I have an extra pair of shorts.
Okay. Let's focus now. I'm done reading my text. we're back up on the board. So they just point out that roughly $2 billion each year is spent on subsidence and foundation issues. And so again, not really dangerous to us, but dangerous to our pocketbooks and something that we will spend money on. And so if you ever get a house, you turn into an old person and you stand out there with your garden hose and you spray things down by your house because you don't want foundation problems because they're really expensive to fix. So examples, minor serious damage to homes, underground water line ruptures, minor major movement in the earth or objects on the ground. So like telephone poles tilting over, fences tilting over, cracks in your house or your foundation. All of these can be a big thing. If you have too much foundation, we don't have this problem in Texas because we don't have basements because it's not a great reason for basements, and we have a lot of hard rock, so they're very difficult to dig. But when you have basements and foundation issues, you get cracks, and you can get like flooding in your basement as water comes in through the cracks, or it can mess up pipes down in your basement area. So that's just something to consider. Linkages between subsidence, soil volume change, and other natural hazards. Obviously, melting of your permafrost can be a big deal. An effect of earthquakes, volcanoes, and climate change can also see your soils change what they're doing. Flooding can have a big effect. Mass wasting can have a big effect anytime your soil gets moved around. Here's a pretty dry crack. Any of y'all get cracks this size in your backyard during the summer? We all get them a little bit, yeah. This one's pretty big. Like you could fall down in this one and probably hurt your leg pretty badly. But we still get pretty big cracks here. So this is just from drying soil. The soil's dried up too much and doesn't like shrinking like that. Although there are many environmental and economic problems, these are also the benefits. It can affect your water supply in a positive way. Aesthetic and scientific resources, so you can go enjoy yourself in a cave for a couple hours or study something that lives down in a cave. And unique ecosystems are a big deal. Karst regions contain the most abundant groundwater supply, provides a critical world resource for groundwater. Caves and karst landscapes are beautiful. They attract visitors. They provide research for scientists. Home to very rare creatures in the case of some of these caves and karst. Real quick, let me just do this one here. Does everybody know about the great blue hole?
Yeah.
The great blue hole is a karst. Great blue hole, which is just a perfect name. Yes, that's the great blue hole. So this is a karst. You can see that it's like dissolved down inside the rock and kind of have a little reef around it. Again, I will swim in the hole a little bit, but I'm not diving like deep down into the hole. No, thank you. That's where the monsters live. But yeah, great blue hole, nice big karst. I think this is near Australia, maybe? No, this is Belize. I'm not ashamed to admit I don't know where Belize is. Is that Pacific Ocean? If I say it in a high-pitched voice, does that make me sound more dumb or less dumb? Pacific Ocean? Where's Belize?
South America. Like,
South America? But is it an island?
no, I think it's on the.
Off the coast of Belize.
I don't remember if it's on the west side here.
I don't see any Belize. Yeah. Oh, there it is. It's Central America. It's just south of the Yucatan, next to Guatemala and just north of Honduras. Okay. Okay, see it, just south of Mexico. So that's where the Great Blue Hole is at, and that is a karst feature. Oh, who's next?
Probably me. You're not really getting drunk this week? I get drunk this every single 6 weeks.
Hello?
Why are they calling me?
Okay, no problem.
Is it
Okay. Yeah, soon to the gym. Yeah. So what humans can contribute to problems associated with subsidence? We can draw out surface fluids, so we can pump water from underground reservoirs, excavate underground mines, thawing frozen ground, restricting the deltaic sediment, altering surface drainage, using poor landscape practices. We can affect all of those. So fluid withdrawal, taking out oil, water, natural gas. If you pump that stuff too fast, the ground isn't going to be able to hold up its own weight, and you're going to have sinking. I think you all remember this picture. I talked about this gentleman, right? Yes. So this was subsidence in like San Fernando Valley or somewhere in California. Maybe it's this Santa Clara Valley. No, it says San Joaquin Valley. Sorry. But yeah, they lost all this land since 1925. This was the land level in 1925. And then 1977, it sunk all the way down here from over pulling from the underground aquifer there. So they pulled too much water out, and the land just sunk right underneath it. So you want to be aware of that and not do that thing. Subsidence from pumping out fluids. This is just a small little illustration, but what they show is they've pumped out all the water. That water is going to occupy some sort of space in the underground. And not with every single rock type will it do this, but with this particular rock type, pumping out all the water has allowed the ground to sink down a little bit. This doesn't look like much, but any amount of sinking is going to cause problems. And next time it rains, you could have a good 3 or 4 inch flood right here where there's never been a flood before, because now the land is actually lower. Underground mining can obviously change how your water flows and whether your land sinks or not. Melting permafrost we talked about. Restricting deltaic sediment, so changing the way that a river flows or where it drops its sediments is going to be an altering kind of thing. Altering surface drainage, poor landscape practices, minimizing subsidence and soil volume change. What can we do to minimize it? Don't do the things that make it bad. So restrict fluid withdrawal, or at least make it happen over a longer period of time. Regulate mining, prevent damages from thawing permafrost. Not a lot you can do to prevent the permafrost from thawing, but you can go and try to keep the damage from being as bad as it could be. Reducing damage from deltaic subsidence, managing drainage of organic and collapsible soils, preventing damage from expansive soils. So just kind of knowing what kind of soil you have and what you need to do to keep it from becoming a problem. Maybe keep it moist all the time. Maybe try to keep it dry all the time. Whatever needs to happen, just be aware of it. Few people are aware of subsidence and soil volume change hazards. It's not covered in the media a lot. We do get a lot of commercials down here because foundation repair is a big business. But other than that, you won't see a lot of news stories on it. It's definitely not an attractive news piece. People who live in dramatically affected areas are more aware than others. So like I said, in Texas, we're aware of it. In other areas, maybe a little bit less so. So obviously, along with all of these, the best solution is just to avoid building in an area that has these issues. So if I have subsidence features, if I have any of the red flags going on, I want to kind of avoid that area if I can. So they get back to Venice at the very end, and I'm going to get through this PowerPoint in one day. How many minutes do I have left? Just a couple, right? 8:27. Yeah, we're doing good. So back to Venice. The city is located on 118 small islands near the center of the Venetian lagoon. The structures were built on wooden pilings and rest on a dense layer of clay. There's actually a really cool History Channel video on this that has been done recently. So it's not too old, and it's got some good graphics. And it shows how the city was built on the wood pilings. It's really, really interesting. So they're already kind of on stilt legs down in the mud. You don't see any of this because it's in a dense layer of like muddy clay. But this whole city literally probably should not be there. The Italian people have studied the subsidence of Venice for decades, kept records for hundreds of years. Changes in water levels are recorded as early as the mid-1860s. Flooding is an age-old problem. The river's diverted to reduce input of sediment. And so here's a picture of it being pretty flooded. Obviously, they have the gondolas, but on the sidewalk, you should not be standing in the water. That should just be a regular sidewalk. And so you see Venice here, built right out in the middle of the lagoon. So again, you're kind of pushing against nature here. This should be a lagoon, whether that's natural land or not. It's probably a number one area you would say, hey, if there was going to be a flood, where's it going to be? Hey, right in the middle of the bay. That's probably where you're going to have a flood at. So this has been getting worse. The subsidence has been increasing. They're having more and more floods. It's not as stabilized as they thought. So they started what they call the Moses Project, a $7 billion project. I think it went well over cost and cost more than $7 billion. And basically they built these big floodgates for the edge of the lagoon. So actually, if I go back here, just 2 slides. Right here, they built the floodgates. I don't know if they did all 3 or just this one right here, but they built these floodgates so when the tide comes in, they actually raise the floodgates and build, it's almost like a water wall, like a seawall. And it's supposed to keep the water out for long enough to keep the floods from coming in and flooding the city. And so this actually got finished. It was very controversial. I don't think it works exactly as intended, and they had quite a few problems actually getting it designed and getting it to work. And so, yeah, this is good. It does help out, but when it fails, it's going to be really bad and really ugly, and everybody's going to remember that you spent over $7 billion to do it, and the city's still flooded. So there's hit and miss with that. So that's the end of Chapter 8. I did get through the PowerPoint in one class period. And real quick, if I can get it, let's see if I can find a video that shows a little bit of the Moses Project. Venice Moses Project videos. So here's the Moses floodgates. So look at the floodgates come up. So they literally like pop out of the water, block the water from coming in the bay. All right, everybody have a nice day.
You too.
Yes. Just leave it here.
Okay. All right, I got water in my desk. Just left it. Not everything. Thank you.
Hello. Stop the video. Stop the video.